Okay, Unit 4, Learning Target 2D. I can use the rational root theorem and synthetic division to factor higher order polynomials. Our example, y equals 5x to the fourth plus 39x cubed plus 77x squared plus 33x minus 10. And the root is given to us as -2. We know that that's the root because there's a semicolon after the polynomial. So our first step is to list the possible zeros. Now the possible zeros are always positive and negative. All of the factors of the constant term, so all of the factors of 10, which are 1, 2, 5, and 10, over all of the factors of the leading coefficient. The leading coefficient is 5, so we have a positive and negative 1, 2, 5, and 10 all over 1 and 5. But we're going to start with the one they gave us, and they gave us -2. So we're going to set up synthetic division with our root. -2 is what we're using to divide by. We do our upside down long division sign, and then we put our coefficients in, making sure we have the correct number of terms. We have an x to the fourth, x cubed, x squared, and an x to the first, so I'm good there. So I should have a 5, a 39, a 77, a 33, and a -10. Now I'm going to use synthetic division like normal, bringing down the first term. -2 times 5 is -10. 39 plus -10 is 29. -2 times 29 is -58. 77 plus -58 is 19. -2 times 19 is -38. 33 plus -38 is -5. -2 times -5 is 10. -10 plus 10 is 0. It should be 0 remainder because we know -2 is a root. If we would have gotten any remainder other than 0, we would have done something wrong. So I'm going to go ahead and put the x's in here because I want to check to see if this particular polynomial that's left over is factorable. I have a 5x cubed plus 29x squared plus 19x minus 5. Can I factor that? No, I don't think I can. So since I can't factor, I'm going to choose another possible 0 from the list that I already made. And I'm going to use the remainder theorem again with synthetic division to see if it is a factor. So this time I'm actually going to try 1/5 because 1 divided by 5 is in my list of possible zeros. So we are going to use 1 as our dividend, as our root, and we're going to divide each piece by 5 as we go. So we're going to use a 1. And now this time we're using the coefficients of the answer. So 5, 29, 19, and a -5. I'm going to bring the 5 down, but I have to divide by 5 since this was actually a 1/5. So I divide by 5, and I get a simplified to a 1. 1 times 1 is 1. I add 29 and 1 and get 30, but I divide by 5, again, because this started out as a 1/5, and that simplifies to 6. I multiply 1 and 6 and get 6. I add 19 and 6 and get 25. I again divide by 5. That simplifies to 5. I multiply 1 and 5 and get 5. I add, I have 0. Oh, cool. 0 means that I actually do have a root here. This is one of my solutions. So yes, 1/5 is a 0. That's good news. So since 1/5 is a 0, I'm going to go ahead and substitute my x's back in here. And when I look at this, I see that I have an x squared plus 6x plus 5. And I know that that is actually a factorable trinomial. So instead of having to continue with synthetic division, I can factor that. So my factors of x squared are x and x. This is positive and positive, and my factors of 5 that add to 6 are 5 and 1. So there's my two factors equal to 0. So my other roots are x plus 5 equals 0, giving me negative 5, and x plus 1 equals 0, giving me negative 1. Okay. On my next example, I have y equals x to the fourth minus x to the third plus 24x squared plus 10x minus 25, and they're telling me the first root is 5. So I'm going to start by listing my possible zeros. My factors of 25 are both positive and negative, 1, 5, and 25, and my factors of 1 are just 1. So my possible zeros are positive and negative 1, positive and negative 5, and positive and negative 25. I know I have a root of 5, so I'm going to use synthetic division in the root of 5 to start. I do have an x to the fourth, an x to the third, an x squared, and an x term, so all of my terms are there. So I bring down my coefficients, 1, negative 10, 24, positive 10, negative 25. So when I do my synthetic division, I of course bring down the 1. 5 times 1 is 5. I add and I get negative 5. 5 times negative 5 is negative 25. I add and I get negative 1. 5 times negative 1 is negative 5. I add and I get 5. 5 times 5 is 25. I add and I get 0. I was expecting a 0 because they told me 5 was a solution. So let's go ahead and put my polynomial out here as an x cubed minus 5x squared minus x plus 5. And then I ask myself, can it be factored? Can I factor that? And actually, when I look at this one closely, I see that yes, I can. I can factor that by grouping. So I don't have to continue with synthetic division. I'm going to factor by grouping. So let's group this. Okay, x cubed minus 5x squared, one group, plus negative x plus 5 is my second group, and we equal 0. My GCF of the first group is x squared, leaving me an x minus 5. And then I'm factoring a negative 1 out of the second group, leaving me an x minus 5. Of course, I still equal 0. Now I have x squared minus 1 and x minus 5 equals 0. When I look at that x squared minus 1, I should have an alarm bell going off in my head because both x squared and 1 are perfect squares. And with two perfect squares and a minus sign, I can factor. So I need two sets of parentheses. The square root of x squared is x. I need a plus and a minus, and the square root of 1 is 1. And then I still have my x minus 5 equals 0. So my zeros then are x plus 1 equals 0, giving me a negative 1. X minus 1 equals 0, giving me a 1. And x minus 5 equals 0, giving me a 5. Now, I was given a 5 at the beginning. So 5 actually occurs as a solution twice. And that's really important. We call that multiplicity, meaning that the same number occurs as a solution more than once. Solutions occurring more than once. So the solutions are negative 1, 1, and 5, but with the 5, we say it has a multiplicity meaning it occurs more than once, of 2, and this is a multiplicity of 2 because it occurs twice.